Very much. I think it's afternoon now. Good afternoon to you all. My name is Hassan Gay, and I'm the Deputy Permanent Secretary at the Ministry of Communications and Digital Economy. First of all, let me thank the Chair, Doctor, for having me, and also acknowledge the presence of Dr. Haidara, and also all stakeholders here present, distinguished ladies and gentlemen, all protocols duly and respectfully observed. All protocols respectfully observed. I am profoundly honored and excited to deliver this important statement on behalf of the Honorable Minister, who extends his apologies for not joining us today due to the need to attend to another equally important event. First and foremost, I would like to put on record our appreciation of this very laudable and impactful initiative. The collective efforts from the organizers demonstrate great will for the utilization of the unlimited potentials of artificial intelligence and data science to provide transformative solutions across all walks of life in the Gambia. As a ministry, we continue to prioritize support to interventions geared towards creating the enabling environment for digital technologies to thrive, and as such, we are very welcoming of events of this nature. We applaud the steps taken by the ecosystem, especially on such an important front. I would also like to thank all of the pioneers and contributors to this great initiative. You all continue to showcase your selfless dedication to the development of ICTs and fostering of innovation in the Gambia. Chairperson, artificial intelligence has become a reality we need to embrace today, and this can only be done if we can put in place the right strategies to ensure our tech-savvy youth reap the benefits from this unprecedented wave of innovation. Chairperson, we are all witnesses to this great deal of impact artificial intelligence tools like ChatGPT has on the various industries this year alone. This, to me, gives us added impetus to accelerate efforts and ensure Gambians become drivers in this space and not just consumers. Equally, data science has become an important value addition to the planning and policy-making process, especially in the global south, which has been crying for more informed and evidence-based interventions over the years. Mr. Chairman, to shed light on the befitting theme of this event, I would like to reaffirm government's commitment to mainstreaming ICTs for better outcomes in the agricultural sector. As you may all be aware, agriculture has been a bedrock of our economy, or in honest terms, is supposed to be the bedrock of the Gambia's socio-economic transformation process. However, its dwindling contribution to GDP and overall development is largely owing to the low rate of innovation in the sector. And as such, I believe choosing this theme is quite important, as it gives us the opportunity to concertedly provide solutions that will not only deliver quick wins, but will eventually transform the whole sector for the good of generations to come. The theme is also in line with the objectives of the e-agriculture strategy 2022-2024 and the agricultural sector priorities on leveraging technology to improve outcomes as outlined in the Recovery Focused National Development Plan 2023-2027. I firmly believe that the challenge going forward for us as a country is to transition from rolling out the usual e-platforms that provide market information for women or give them access to markets, to focus on devising strategies to help us deploy artificial intelligence tools for better forecasting, pest and disease control, and overall greener yields. I therefore have utmost conviction in the fact that this workshop is quite timely and will help enhance local capacities in these game-changing areas, and it will also help drive the much-needed paradigm shift when it comes to embracing and interacting with advanced technologies for more cost-effective and efficient locally driven solutions across all sectors of the economy. In conclusion, I would like to reiterate once again that this workshop is of huge significance, and I expect its outcome to be as meaningful and impactful to our socio-economic transformation process in the medium to the long term. With this statement, I would like to declare this 3 days workshop officially open, and I thank you all for your kind attention.
So I want to talk briefly about applications of deep learning in agriculture. And yeah, maybe just a small brief about SANBAT. So we are a non-profit that's based in Uganda, and our goal is really leadership in AI for social good. So the key things there are a social good and African context. And we use AI to generate evidence for policy. So we want policy or information supported policy making, and also want to contribute to the AI policy. How is AI used in the African context for social good? And why social good? So yeah, this is a slide that is also very important for agriculture. So of course, humans have intelligence and want to do good. This is hopefully what we all want to do. And AI, in many ways, can amplify what we call human intelligence. And so the idea with AI for social good is really to scale the amount of good humans can do. And this is what we try to do with AI. And everything we're going to discuss, deep learning, of course, is part of AI and machine learning and everything. And Africa is uniquely positioned to benefit from AI, particularly for social good initiatives. I think that's why there's IndabaX, there's the big deep learning INDABA. There are many things like Data Science Africa to bring communities in Africa to sort of talk about the things that are of importance to us and apply some of this cutting edge technology to them. All right, so that's really what SANBAT does. I'll jump into the topic of today. So how do we see deep learning or machine learning generally as a solution for problems like agriculture? So in agriculture, you can view most problems in agriculture and health as sort of a pipeline view of the challenge. So there are challenges, and there's already work being done in this area. You have experts in agriculture, you have the farmers. There are already things they've been doing. Since the agricultural revolution, things have changed, and they've been refining their processes and how they do inputs into farming and etc. So there's already stuff going on, and it will continue going on. What will come with from the computing side, computational side, is how do we improve this pipeline? And how do we do that? By looking at these areas where the rate is limited, where there's inefficiencies in this pipeline. And we try and figure out those places where AI or deep learning or machine learning could be of help or could be useful. So this is very, very important to understand, particularly about agriculture, because there are many problems where the solution is really a human solution. You need better managers, you need people who can plan better. And then there are certain problems which are uniquely AI or machine learning type problems. So it's very important to distinguish which those are and to target the right technology to the places where the rate limiting can be solved by AI or machine learning or deep learning. All right. So, and in agriculture, you could think of sort of two broad areas where rate limiting could have a highly negative impact. So one of the broad areas is planning and monitoring. So this really is in how do you get data from the farm or from the inputs, and how do you plan with that data, and how do you do monitoring after you've done interventions on your farm? How do you monitor these things? So this really first part is about data. How do you collect data about activities in agriculture? Second part is, okay, how do you automate certain things? How do you automate certain tasks in agriculture? So we'll talk about these two things mainly, broadly. So maybe one other distinction is sort of this idea that instead of looking at when you say agriculture, it tends to be a bit limited, but you could think of it as agri-food system. So this is the whole value chain of agriculture. Where does it start and where does it end? So you need to understand that whole pipeline, or at least look at things in the context of the whole agri-food system, the pipeline. This makes it easier for you to understand where these rate limiting tasks are and where you can apply computational methods or tools. All right, here is a depiction of what a typical agricultural value chain would look like. So the first part up is really the value chain. So you can see from you start with the pre-planting or planning. There's some planning that the farmer has. If he has a bag of seeds, he has to plan how many, what crops am I going to grow? What animals am I going to put on my farm? How will I space my crops? Will I intercrop? Will I not? Land preparation, then you can sort of see all these activities. Seeds, farm management, harvesting, aggregation, pre-processing stage, storage, processing, then post processing storage. So you have storage there. Then all these things, packaging, warehousing, end user transport, then retail, right? So this is the whole chain of value where value can be created in agriculture. So what we normally look at, which is very limited, could be something like farm management. This is where you may look at applying AI, but you can see in the whole process that it's important that you think through it, and each of these places you can sort of think, okay, what would be the role of AI in this place? So that's the top pictorial. The lower one is sort of the things I've been talking about. So you can see these phases or these categories: planning and monitoring, right here on this vertical axis, and then in this horizontal axis, it sort of shows you the stages of the key stages of value of this value chain in agriculture. So you have planning and production, sort of the first things. Then after you harvest, what do you do in post-harvest? Then what do you do when you want to talk about distribution and logistics? And for each of these sort of phases, you can see the areas where, or sort of the big activities that happen, where you can sort of try to intervene with AI and automation and machine learning. So what we want to do is basically talk about these. So the first part of the talk is really talking about these aspects here and sort of where applications of deep learning or AI automation in these areas. And really it will be giving a bunch of examples. Then the last part of the talk will really be going into one of the areas, sort of drilling down a bit and talking about deep learning. What does it mean when you apply it to this area? So that's sort of the rough outline of the talk. All right. So maybe the first area. So we have areas. So this whole phase of planning and monitoring is really a lot of it has to do with collection of data. So one area is genomic innovation. So this is one area where you can apply computational methods, AI or deep learning. And I give some examples. So for example, this example down, for each of the areas, I give sort of a use case of organizations that are already using this, have farmers registered, have they're making money off this. So they have established companies doing this already. And so one of them is this thing called egogenomics. So genomic innovation is really, so for example, egogenomics, this one is really a platform for collecting and sharing genomic microbiome data. So microbiome data or microbiomes are sort of these organisms that live in the soil. And you want to understand how the interaction between those and, for example, pesticides or fertilizers And so Genomics creates this platform where they collect all this data, and then that data is used for things like if you're a big pesticide organization or fertilizer organization, then you can sort of look at the data, see how that reacts with your, at a genomic level, how it reacts with your pesticide or fertilizer, and then you can do prediction of how well your fertilizer will do, what's the long-term effect of applying this fertilizer or pesticide to the soil, wherever you're going to put it. Right? So this is an area where, again, this is planning and monitoring. So it provides you data that you can use for planning how you're going to, for example, manage the soil in your field. Another example is, so this aspect of digital on-farming extension advisory. So I think extension services are services where the government, they tend to be run by government, has experts who are located close to the farmer, in this case, smallholder farmers in Africa, and they provide the extension advice or advice on what to plant, when to plant, how to handle pests and weeds. And so you can automate that process. Instead of having an individual go around the farms, you can say, okay, you can make this digital, use a mobile phone. So this Ethiopian Agriculture Transformation Agency, so this use case uses IVR, so that's voice and SMS hotlines for scaling access to extension workers. So they can call into some server, and the server can give them information about some pest or disease. But what's interesting, the AI part here is that they combine this data with location data, with satellite imagery, and use that to send back prompts or alerts to farmers that in this area of yours, we see that there's a lot of questions about this weed, la 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 la. Here's some advice coming up from the center, maybe new varieties, new inputs, this kind of thing. So there's a space for using AI to bridge this gap between the experts who are maybe located at the center of town and the different farmers, and they use this using phones, smartphones or feature phones. All right, the next use case here in planning and monitoring is farm health monitoring. So this is the most common one. How do you monitor the health of plants? And one idea is, or one use case is this app called Plantix. There are also several other apps in Africa. This one is based in India, which India is very close to Africa in agriculture, for example. So this does mobile diagnostics. So you take an image of a crop, and then the app does diagnosis for disease, for nutrients, etc., etc. And then it can provide some sort of intelligence, maybe prediction of disease, prediction of pests. They also go further and do things like determine what type of inputs you may need into your farming, into your farm or agriculture garden, etc. So that's, again, a good example of AI deep learning being used commercially in agriculture. When you come down to automated actions, so these are processes where you're automating direct actions that happen in the field. You have e-fishery, which is, I think, Indonesia or so. But there are also several examples in Africa. And this one uses IoT to determine the feeding of fish. So you have in aquaculture where you're cultivating fish, this particular organization has sensors that they put on the feeding mechanism to understand, how much should you feed the fish, how much has been consumed, and you can do this remotely. And they use a bunch of AI with the IoT sensors to pick sensory information and then process it and then understand how to feed fish, the shrimp and all manner of fish that they use. All right, then you have also things in alternative credit. So here, this is using AI and deep learning and machine learning to sort of bridge, provide credit to farmers. So if they want to buy seeds, they want to buy pesticides, they don't have money, they can get money from any fintech, any microfinance, any small bank, And the way they do that is using this credit scoring. So the credit scoring basically takes alternate data, for example, their history of using banks or maybe telecom data, etc., and calculates a credit score for each of the farmers, and then they can use this credit score to get funding, for example, from Dana. That's what Dana does. It sort of does credit scoring. So again, this is using AI and combining it with a bunch of data to come up with one score for the farmer. So you're automating this idea of credit. Insurance, Acre Africa provides insurance services to farmers based on the weather data. So you can buy insurance from this to 1 acre fund, and what they do is that when they use their weather data to estimate sort of what insurance you have to pay, right? And if you have a bad season, then they can refund you some money. Or if you have a sort of mediocre season, then they use AI to try and capture like what yield you have and determine, how much should be paid for the loss in yield and these kind of things. So pretty good use of AI. The last example is sort of this matching people who have tractors with farmers, right? So you want to make sure that, so what this Hello Tractor does is it's a platform that enables the owner of a tractor to be matched with a farmer. So what it does, if there are many farmers in one area, then it can sort of match these two people and say, if I send a tractor, it's going to do these farmers in this area because of their proximity, and this kind of thing. And the farmers do a pay-per-use platform. So it has to be able, the tractors tend to have sensors, IoT sensors that calculate how much work it has done in a particular farm. And all this is AI. Even the matching algorithms, you can use AI to do that. So several examples, basically, and all these are these are just a few of the examples, but each of these areas you can sort of see how AI could be used to better the process. So either for collecting data, for planning and monitoring, or for automating some expert tasks generally. So yeah, so that's sort of the broad overview of how AI and deep learning is being used currently. Of course, there are many, many more examples, and in my references, I cite the report where even many more use cases are. So you can sort of go there and see how they're using it. So in terms of how you as a group you can use this, you can also take these aspects and say, okay, how can I build something that could address this particular problem? Could be digital financial advisory, farm health monitoring, etc. All right, cool. That's sort of the first part of my talk. The second part is to sort of make it more real. I think Dina presented a good use case of poultry. I'll do one which is very similar to what she did. This is sort of diagnosing diseases from images, and I'm sure probably a lot of you have had this. But in about 2015, 2014 or so, we started working on a project to diagnose disease of cassava in the field using smartphone by taking an image of the plant and then from the image calculating some sort of statistics or information that you can use for planning. All right, so I know you have sessions in the next 2 days on machine learning and deep learning and computer vision. So I'll keep this fairly high level. So what you want to do, of course, with machine learning is to enable these programs on the mobile phone, for example, to learn, or tools or computers or whatever, to infer from data, to learn and infer from data without explicitly programming these tools or these programs or these applications. Right? This is the whole point of machine learning, that the machine learns without being explicitly programmed to do something. And this is quite different from ordinary programming, where you program, I want this thing after this step, to go to this step, to this step, to this step. Here you want to empower the a program or an agent to do this by itself. And there are many examples, which I'm sure many of us know. But the key ones that you always use are the ones on your phone. When you do a web search, be sure you're using some machine learning model or deep learning model that's sort of returning all these queries. We've recently been talking about ChatGPT, and how it's so exciting. Again, good examples of deep learning and machine learning, and many other things, self-driving cars, etc., etc. So all these agents or programs that are programmed with data, you provide data and they self-learn, or they sort of learn without being explicitly programmed to carry out whatever action they're built to do. All right, and generally, or more often than not, in agriculture, you will talk about supervised machine learning. And the key thing here is that you have data that you're using to train the model, and this data is labeled, which means you have input data, some type of data. It could be images, and then you also have a label, right? So, for example, in our case, for diagnosing disease from images, how we'll train this model is to have images of leaves, several leaves, and for each image, we have a label saying this is healthy, or this is disease 1, or this is disease 2. So this is a labeled data set. And what you want to do is show the machine examples of this data, and hopefully it learns a function that associates the data, the images or video, or whatever, with the label. This is the whole point of supervised machine learning. And that's what, fitting a model or modeling is all about. All right, so I guess the key point here, where deep learning comes in, I think the key point of deep learning sort of comes from representations of data. So in this process, you need to be able to represent data in a certain way, right? So you have to think of, if you have images, if you have video, if you have texture data, if you have numeric data, you have to find a way of representing the data so that it's computable, right? So you can compute over the data, right? So it's in number forms, and you can sort of compute over it. This process is called representation learning. So you have to learn a representation from the data you have. And the representation is really just a vector from your input data. Given an image, I come up with an input vector or some sort of vector that represents, so it's called data representation, represents the leaf, right? And you use that data to build your model. So for this particular example, this is really an example of computer vision. So using images or video data as your input data, learning representations from the images or video, and then using that to train a model that can do, for example, diagnostics. That we're talking, the example we're talking about, given an image of a leaf, how can you say this is diseased or not? Yeah, so you have computer vision, I think, tomorrow, so I'll not dwell on it much. But I think the key thing here with computer vision is this idea between whether you have a global representation of the image of the leaf, for example. A global representation basically means that you have a representative vector that represents the whole leaf, or you have multiple local representations. And this is what I sort of mean by that. So if you look at this, the picture on the left, when we started out in 2012, 2013 or so, we're using a package called OpenCV. Still used now, but this is the way we're doing it is fairly old school now. But what we had to do was calculate these things called local features. So you had to, if you look at this image, so this is an example of an image, and these dots here, these pluses are key points that identify the deformity in the leaf, right? So the sort of the edges of the leaf, right? How deformed it is, the texture. So you have things like sift features, they used to call them, or orb features. And if you look at the one down here, these are orb features. So it identifies interest key points. So points on the image that are of interest, that are exciting. For example, if you look at this image where it's decolorized and it's sort of bent, you have interest key points. And so by getting these are sort of called local representations because you can get very many per image. The image on the right are examples of global representations. So you take the image and it returns one vector, which represents a global feature, right? So things like color. What is the general color of this image? Right? So you can have color histograms, representing the whole image. But the key thing here, the key point of this is that you had to have some idea, some domain knowledge of your problem, right? You had to know my cassava leaves, when they get sick, they get deformed on the edges. So I need to look for features that represent the deformity in the leaf. If you look at the down thing, you can see this is a diseased leaf and it's sort of decolorized, right? It used to be green. Now there's a bit of yellow here. And so you'd need to know that, okay, my leaf, which is diseased, has certain colors that are different from a healthy leaf. And so you need to figure out how to pick features of color, right? So you as the domain expert, as the person building the model, you had to explicitly write these features, get these representations out of the image. And yeah, I'm sure this would. So you had a process like this, right? So you have raw data, and you had to figure out which features you want to extract, get the visual representations or whatever representations, then train a model, and then sort of with the trained model test how well it does on previously unseen data. So this was problematic, right? So you had to, extracting features was quite problematic, because then if I had more knowledge than and so you had to learn these representations, you had to build them yourself. And where deep learning comes in, so deep learning is a sort of a subset of machine learning. And what you want to do is to have a process of representing data that does not rely on the expertise of the person building the model in some way, right? And this is what deep learning generally offers. It offers the ability to extract representations of your data without you explicitly highlighting what features are of importance. Right? So I hope that that is clear. That's a key point in why deep learning, deep neural networks, or deep learning is slightly different from most of the other machine learning methods. All right, so here's our task. Our task was really given some data, and this was the data we had. You had 4 diseased plants and 4 diseases, categories of diseases. You had a 5-class problem, 4 classes of diseases, and one healthy class. And so basically to train a model, we had to collect a lot of data, examples of each of these classes which are labeled, and then use this to train a model. So how does deep learning work? And so basically, the key thing, at least for computer vision, is these things called convolutional neural nets. So I'll just talk about it from the point of view of data representation, feature extraction. So the beauty with this one is it's called deep because it has several layers, a layered architecture with multiple layers of neurons. And what it does with feature extraction, basically you can come from pixels, which are what you see in an image, then you can start. the different layers extract different abstractions of the features, right? So you can come from pixels, you can identify edges, the edges combine to form object parts, you know, for example, eyes or whatever. And then from those object parts, you can get object models, right? So this is an example if you are sort of trying to identify features of a face. So this is how it would do it automatically. Back in the day when we did it by hand, there were very interesting ways of extracting features, for example, from a face. For example, you had to try and extract out the eyes because the eyes are unique. They're sort of the same kind of thing, layered by a certain bridge and covered by a certain bridge on top as well. So you sort of have to figure out ways of writing that. Then the nose, the mouth, the ears, which are equidistant, and these kind of things. You had to manually write in these data representations. But with the deep neural networks, you can sort of pick them out for free. And this is a key advantage of deep learning as a subset of machine learning. All right. So yeah, basically that's this was the task we had to do, and my initial thought was for us to walk through a quick example of building something quick online. But given that time and you may not have your machines there, I leave this as an exercise. So I'm leaving a bunch of tools here, but I'm sure these will come up once you've started doing the tutorials in the next 2 days. But I leave a tutorial. This is a notebook collapse of an example of taking this data that we have and building a model off of it with examples of how to leverage a bunch of tools. So things have improved quite well, quite fast. And so the idea really is almost the mark of a good data scientist now is that you know what the right tool to use is. You have several tools you can use to sort of play around with these techniques. One cheap and quick one is this model maker. And I give an example here. This is one I thought we'd quickly go over. But this is something that's very easy to do. I think it's called Teachable Machines. It's a Google product where you can just drag your images, you specify which classes you want, you can drag a few samples, you can upload, or you can check them by a webcam. And then you can decide on training a model. You can train a model. It's all click. There's nothing like coding. You can train a quick model, and then you can even evaluate the model, right? You can upload test images, and then you can see how well your model works. So this is a very quick and dirty way to build a quick model if you wanted to evaluate something very simple like a computer vision task. So yeah, I would encourage you to, if you go to this link here, you can get some of the data we used and the different diseases, and you can try out this tool or try out a bunch of other things if you're keen to do that. Yeah, I think that's really it from my side. Yeah, thank you.
All right, thank you very much, Ernest. That was great, as usual. Let's have a question. Okay, as a chair, I start. So my question was, yeah, to go a bit deep on your cassava project. How easy was it to work with the farmers to either collect the data or get them test your tool?
Yeah, thanks a lot. So farmers are quite interesting to work with. So just a small story. So there's we once were talking. I was talking to a farmer, one of the farmers, and I was asking him, why is it so hard for you to take up new technologies, even technologies which are not based on IT? So even just new seeds, for example, new breeds of cassava. And he gave me a little story. He told me of one time they had a cassava variety that they were planting, and it was a bit bitter. And so the state gave them cassava varieties that are sweet. They're very sweet, they grew fast, and they planted them. But after some time, they stopped planting them. And the reason they did that is because very, very unintuitively. So he explained to me that when they planted the sweet varieties, their wives went and dug them out quickly once they were ready for harvest. The wives would dig out everything and sell and eat everything and sell them because they were sweet. And the problem with this is that in hard times for food security, then they wouldn't have any cassava. And this was very unintuitive. I mean, no one would ever think. So what they decided to do was to plant the bitter variety, which takes long, it has a bit of pace. But the good thing with that one is that then their wives would not pick it out of the ground quickly. They wouldn't sell it very easily. So he was assured that his family had food for a very long time. So it's very unintuitive. I guess what I'm trying to say is that working with farmers is quite complicated. You may not have the same metrics. You may think you're trying to help them in one way when actually they don't think of it as being helpful. They have a sort of another objective measure they're optimizing. One other small thing was with working with the agriculture organization here in Uganda. So initially we had created a tool to automate data collection. And we thought this was a great tool for them. It saves time, saves money, but then giving them the tool means then the people who are going to the field don't go to the field, the drivers don't get fuel, people don't get per diem. And so they had to fight. They fought the tool. They wanted to keep using paper. And so there are very unintuitive ways in which technology fails to be used, not because of the technology, but just because of the social problems around the whole thing. So yeah, working with farmers is a touch and go, but I think it's very important to understand the sociology around the farmers and their situation. Thanks.
Yes, thank you so very much for that insightful presentation. My question will be, when you're developing or building your machine learning models, okay, how do you ensure when you're building your CNN models, how do you ensure that the accuracy level is at a very good level or rate? Or the loss, how do you reduce the loss? How do you make sure that the loss is really low or the accuracy level is very high? Thank you.
I'll tell you are the ones which you may not find necessarily on online tutorials. So you want the model to be robust. It's not really, so there are two things. One, the accuracy or the loss. What you want that to relate to is what it relates to in real life. So if, for example, you want to understand if a farmer takes a photo and it identifies it as a disease, when it's not a disease, what is the effect of that penalty relative to if it's not a disease and they identify it as a disease, right? So you want to make sure that that sensitivity or the specificity is, you understand it basically, right? So for example, we had a disease, one of the diseases in cassava brown streak disease. The recommendation from the ministry, if you see that disease, then you uproot the whole garden, right? So if you're building your model, you want to make sure that this particular class is treated quite well. That, you know, when it says there's cassava brown disease, that is very accurate. And then you can lose some, you can afford to have a penalty on other classes because of, you know, maybe they are a bit less mild, right? So if there's, for example, cassava mosaic disease, then okay, yield suffers a bit, but you don't have to uproot the garden, right? So these are considerations in real life. The other part is robustness. The second part, what does performance mean in terms of robustness? So one story is we took the app, it had, I don't know, 96 or 90, what was it, 92, 93% AUC. And we gave it to a deployed app to the farmers. And what the farmer did was to take an image of his wife, right? And they took an image and the app returned that this is cassava mosaic disease we see cassava mosaic disease, etc., at a probability of X. And, this is, of course, the farmer says, you see, but your thing is not working. This is a picture of my wife. It can be a picture of cassava. But in our thinking, we thought, of course, the farmer should use it on cassava. But, the farmer is not, he's taking the sky, and his immediate impression is this does not work. And so one other thing we did was to add another class. So you add a quote-unquote unknown class, a class of so many other random images, so that when he takes an image of his wife, it should say unknown or unknown disease, or this is not applicable, or whatever. So this, again, you won't see it unless you go and sort of deploy this with the farmer. Yeah, and then, I think maybe the third one is sometimes it's good to give probabilistic outputs. So you want to tell them that this is a cassava mosaic disease with X number of probability, and by again, depends on your audience. Can they understand what probabilities are, this kind of thing? So anyway, a few tips on what performance means for these kinds of algorithms.
Thank you. Go ahead.
Doctor, thank you so much for that wonderful presentation. You touched on post-harvest during the initial stage of your presentation. And I'm sure post-harvest, looking at the concept, it has largely to do with technology, because when you harvest normally, certain technical practices are involved, and nowadays it involves heavily, it mainly involves using machines or using technology. From the locally practice of post-harvest, that is normally using the locally made. When you harvest normally, like the tomato, when you want to preserve it, you normally spread it and sprinkle water on it. But nowadays, certain technology can be heavily involved to reduce the loss or to handle it properly. I want to know whether AI is also into that. That is, specifically for vegetables, when they are normally harvested, is AI normally involved in its post-harvest handling, comparing it to the locally one, that is the locally handling method of certain vegetables. Because normally they are perishable. Vegetables normally most of them are highly perishable. So is AI that sort of using technology or using certain deep learning method to make sure that the post-harvest the crops that are highly perishable are handled in the post-harvest manner?
Okay, sorry, you were breaking a bit, but I think if I understood the question right, was how AI can be used in post-harvest, particularly for vegetables, in an environment where also local methods are being used. So I think one key thing is context is very important, of course, and this is where you have. And this is where I talked about this idea of a pipeline view of things. Where in this pipeline, in this current context, people using, do you have inefficiencies, and where are the places where it's a right match between the problem and a computational solution like AI or IoT. So it's a very key thing to get. Otherwise, then you will keep looking for a solution for a problem that may not be the big problem. So I think what I've really seen here, I haven't seen much. I haven't done much work in post-harvest, but I think some of the things I've seen are mainly things like monitoring, right? So you want to probably monitor things like moisture, or maybe one thing we did. Well, but these are not vegetables. For cassava, you had we were trying to understand how necrosis, right? So once you leave cassava for a while, then it starts rotting, but it rots from the center of the cassava, right? So if you cut the cross section, you can sort of see a percentage of the flesh that has necrotized, right? And we're trying to understand post-harvest. You know, they were storing. Some were stored in polythene bags. Some were stored in different areas, and we're trying to understand of the storage, different storage methods. How can you calculate the extent of necrosis over different days? And for this, we're using AI. We're using segmentation methods. Given a cross section of a root, can you find the percentage necrosis? And so really AI could be in these cases for information, right? So if it's for vegetables, normally what I've seen is people use IoT sensors to either measure the temperature or adjust the temperature or measure things like humidity. I've seen some attempts at doing weighting. How do you weigh your post-harvest produce, right? Because weight is an indicator of many, many things. How can you weight something from an image, for example, or measure size from using an image? So yeah, I honestly can't say I've worked in that area, so I don't have many examples. But I think the key thing really is that given if there's a local problem, a local way they're handling it, there's some context. Is it easier to improve this context? Or is it easier to just pull out the whole context and apply some sort of new system? Or is it easier to augment the system? Maybe you can measure temperature or humidity much better with an IoT sense in the local environment. I guess that's what I would say. The other things people are automating around this is ways of storing in different amount of containers, but this has little to do with technology or computational technologies. Yeah. So sorry, it's not a very direct answer, but yeah, hope you get the sense.
Thank you, Dr. Ernest. I have a quick question on how you apply AI in planning. Probably you might not have applied this in your specific context, but I am interested to know how easy it is to develop some kind of dynamic AI to help with changing real-world environment. Let's say, for example, in agriculture, I'm currently doing research on how you can develop some agricultural seed management databases that can be used by agricultural seed technology to help them to identify which particular seed will do well in a particular soil, right? Because different soil conditions can determine how different seeds can perform. But one of the problems that exists currently in the seed technology environment is that a particular seed can do well in a particular soil this year, but then next year, the same seed will not do well in the same soil environment, right? And in that case, one may be thinking about how you can develop and train some AI tools that will be dynamic to respond to the changing real-world environment. I'm not sure if you have any experience in that. Thank you.
Yes, thanks for the question. Yes, that's a very interesting question. So we did some work with a big project that was looking at cassava breeding and how to automate that with AI. And I think how we're using it, how we were using it, especially because it's dynamic. I think they had a slightly less ambitious goal. Their goal was to decrease the breeding cycle time. I from 6 years to maybe 4 years or 3 years. And how we're using AI in that place was to look at the phenotypes. So the different environments. So you can have trying to link the genotype, because normally I think they were using the genotypic information about the breeds to do the selection. I think this is, I think, what you're trying to say. How do you develop different seeds for different environments? And what they were using the AI for was really the phenotypes. Can you match the phenotypes? So how the different seeds express themselves. So things like, does it get diseases quickly? The size of the tuber in this case. And so that's where we're using AI mainly, phenotypic information. And then what they were doing in the reverse, at the back end to handle some of that dynamic nature of the process, they were using AI to take genotypic information, add the phenotypic information, and then start predicting which of the seeds should go to the next round of breeding, or how to select seeds from this combination of data. And so they found that using AI provided better, better predictions of which seeds to select for the next round of breeding. So yeah, so it's not. So yeah, I think sort of the general point here is that I think to identify small goals where AI could be useful. In this case, it was very useful for doing the phenotyping, capturing phenotypes. So not really in handling the whole dynamic nature of getting good seeds, but maybe just one aspect of getting more information that is accurate. And so maybe that's one way of looking at this thing. Yeah. Thanks.
Thank you very much. You've given a wonderful talk and answered adequately most of our questions. And one request is, can we have your slides afterwards that we can share with the participants?
I'll send them through to you, yeah.